We're going back to our pancake analogy here. So, if you remember our recipe, we had 1 cup of flour, 2 eggs, and a half teaspoon of baking powder gave us 5 pancakes. So, let's say we had 4 teaspoons of baking powder, 10 eggs, and 3 cups of flour in our kitchen. If we followed the recipe, and that is the key thing here, no cheating, no saying, 1/2 eggs is fine. No, follow the recipe. If we follow the recipe, how many pancakes can I make? Well, if I use up all of the baking powder, I have enough baking powder to make 40 pancakes. Because remember, I have 4 teaspoons, and I only need a half of a teaspoon to make 5 pancakes. And so that would work out giving me 40 pancakes. If I use all my eggs, I have enough eggs to make 25 pancakes. Because I need 2 for every 5 pancakes, and I have 10 of them. So I can make 25 pancakes. But if I use up all of my flour, the point at which my flour is used up is when I have made 15 pancakes. I only have 3 cups of flour, and I need a cup to make 5 pancakes. So the flour is what I would call my limiting reactant in terms of chemistry. The limiting reactant, sometimes called the limiting reagent, by the way. Reagent is just more of a fancy, sciencey way of saying reactant, as if reactant isn't sciencey enough. So my limiting reactant or limiting reagent is the thing that runs out first. And it's as simple as that. It's just you have everything that you need for the reaction to go, to start happening. One of those things is going to run out first. You're never going to measure something exactly correctly where you have the exact right amount of everything to start off with. And truthfully, honestly, most of the time, you don't want to have exactly the amount that you want or that you need to not waste anything. Usually, actually, what happens is if you're doing this in a professional situation, so you actually, like at a chemical plant, they don't try to get everything just perfect so that every last bit of everything is reacted. Instead, what they do is they make sure that they put in plenty of the cheap stuff so that all the expensive stuff gets used up, because they can bear to buy a little bit extra of the cheap stuff because that's a lot more cost effective than accidentally wasting some expensive reactants. So truthfully, you don't even want a situation most of the time where you have exactly the right amount of stuff. You want to have one thing get completely used up, and that is your limiting reactant, which again, in an industrial setting, would usually be your most expensive thing that you're using. So, once we know what our limiting reactant is, the thing that runs out first, the theoretical yield is what we call the amount of product that is made when that limiting reactant is used up. So in the case of our example here, the theoretical yield is 15 pancakes. So when our limiting reactant is used up and it produces as much product as it can, that amount of product is our theoretical yield. It is the maximum amount of product that we can make given the materials that we started with. That is our theoretical yield. Most chemical reactions, however, are not perfect, and so while you might have a theoretical yield that you theoretically would get, in reality, most of the time you get something less than that. So you might, for example, expect to get 10 grams of a product and only end up making 8. In that case, this 8 grams, what you actually made, is what we would call the actual yield. So the actual yield is the amount of stuff that we actually produced when we did the reaction. So the actual yield is something that will always, always, always have to be given to you unless you are literally in the lab doing the experiment yourself. So because the actual yield is, I actually went out and did this, and this is what I actually produced. So it must be given to you. It can never be calculated. An actual yield can never be calculated. All right. So then to compare our actual yield and theoretical yield, we can use the percent yield. And the percent yield is just what it sounds like. It's just saying how close did we get to the theoretical yield. So the percent yield is just the actual yield divided by the theoretical yield, what we were hoping to get. So what we actually got divided by what we were hoping to get times 100%. And we would like to get as close to 100% as possible. So from the previous slide, we said that we wanted to make 10 grams. That was our theoretical yield. 8 grams is our actual yield. And so if we do that math, it's 80%. Pretty straightforward math there. 80% yield. Which in some situations is good, and in other situations is really bad. If you're working in an industrial setting and you go to your boss and you say, hey boss, I want to start this new process and it has 80% efficiency. Unless you are working in some very highly specialized field where it is extraordinarily difficult to get a good yield, your boss will laugh you out of the room. In an industrial setting, you're going to get well over 90+% yield. You're never going to get 100. That's just not really possible. But you can get really close because those processes are highly, highly controlled. And they have been studied and perfected over the years to get as close to 100% yield as possible. Okay. So let's go ahead and do these practice problems here. Actually, no, I take that back, because this will turn into a really long video if we do all those. So now that we've discussed those things, we'll save the practice problems for those topics for the next and I believe last video in this chapter. So in the next video, we'll go ahead and do these 3 example problems and look at the conceptual checkpoint as well. That way we won't spend, because these practice problems tend to be a little bit longer than normal ones, as you saw from the previous video. So I will see you in that next and last video for Chapter 8.